Hello everyone, this is W8BYA, and we're coming up on Christmas time 2016, and I just wanted to share with you the latest addition to the ham shack here. Real quick story on this Siglent SSA-3021X spectrum analyzer. I was recently laid off from the defense industry after about 30 years, and I've been having to get rid of a lot of my test equipment to help bring in some extra money and things like that. And so I had a couple of spectrum analyzers, and they were my pride and joy. I had a HP 8591E that was fully loaded, with tracking generator and all the bells and whistles, and that was a beautiful instrument. And also had a Big Bertha 8566 that went up to 22 gig, and beautiful instruments, but we had to sell them recently, like I said, to bring in some extra income. Well, I was feeling pretty down about that, and my wife noticed that I was reading my QST magazine, the December issue, and they did a write-up on the Siglent spectrum analyzer. And to be honest with you, I didn't really know about it. And after I read the review, I said, "Oh my goodness!" I started highlighting certain things about it in the article, and I had some questions, and I made a phone call to the Siglent people there in Ohio, and I'll tell you what, I was really impressed. Just within a very short amount of time, I was talking to some very nice and knowledgeable people who were able to answer every one of my questions. So I applaud them for knowing their product, and being able to talk to somebody real quick and very responsive. So having said that, I told my wife I kind of wish I could have one of these, and bless her heart, she went ahead and was able to come up with some money somehow. I don't know how. And she asked me if I wanted to have this spectrum analyzer for my Christmas present, and actually for the next 10 Christmas presents. I said, well, of course. So, gosh, within a week, I had this delivered, and I'm just now playing with it, and I fell in love with it. The display and everything is really to die for. Super sharp, beautiful color display, and the spectrum analyzer is very responsive and extremely accurate. So what I want to do, I just want to show you one of the neat functions on this. To the vast majority of people, this is going to be no big deal, but I just want to show for some of you who are not familiar with a tracking generator and a spec an, how useful it can be. So what I want to do is I want to show you how to measure the frequency response of a couple of different filters I've got lying around here using this instrument. I'll show you how fast and easy it is to do so, and how accurate it is. So anyway, I'm going to get on the other side of the camera, and we'll leave this thing in the record mode, and hopefully you'll be able to see what I'm doing, and you'll be able to see what a cool instrument this Siglent really is. So let me get started with that. All right, so first things first, right out of turning the unit on, it starts sweeping right from 9 kilohertz up to 2.1 gigahertz, and defaults to a resolution bandwidth of 1 meg, and it just floors me how sensitive this SPECAN really is. I've got a filter here, and I wonder, let's see. Yeah, I should be able to see it. It's a Microwave Associates. It's an old end connector low pass filter. Has a cutoff of around 500 megahertz. So let's just use this to see what the frequency response of this filter is. We'll be basically generating what's known as a like a Bode plot, just frequency response versus amplitude versus frequency. So incredibly easy to use. We hit the frequency button, start frequency 0 hertz. It's really 9 kilohertz. Stop frequency. For this guy here, since it's a 500 meg low pass, let's punch in 1 gig. So it's that easy. 1 gigahertz is the stop frequency. Divisions are 10 dB per division along the y-axis, and what floors me is the how sensitive the instrument is. I don't have the internal LNA enabled. It's off right now, and even so, with a 1 meg resolution bandwidth, we're already almost hitting minus 70 dBm for the noise floor. And you can lower that. Just hit the bandwidth, resolution bandwidth shows up, and I can just bring that down very, very easily. There's 30 kilohertz. I can bring this down, believe it or not, to a 10 hertz resolution bandwidth, which equals the narrow bandwidth on the HP 8566, and that allows you to see very, very closely spaced spurs and signals and modulation, things like that. So it's a very, very powerful machine here. So what we're going to do is, first things first, I've just got a couple of jumper cables here. These are just short RG223 jumpers, and we're going to hook up the tracking generator output port, which is here on the left, and this is the SPECAN input, RF input port on the right. I'm going to leave the default the input attenuator set to 20 dB. That's fine. The reference level along the top is 0 dBm. That's also going to work just fine for what we're doing, and we don't need more dynamic range than minus 70 dBm or minus 70 dB dynamic range, so we can leave the bandwidths just the way they are. So what you do is you enable the tracking generator by hitting the TG button. Default level comes up as 0 dBm. That's fully adjustable, but for what we're doing, 0 dBm is just fine. And to go ahead and turn it on, we go ahead and turn it on. The sweep progress is shown along the bottom, and there is the tracking generator output along the top, right at 0 dBm, which is where it's supposed to be. What floors me is how flat and accurate that TG output is. You can just barely make out some slight irregularities, but for all practical purposes, I mean, it's right on. So what we want to do, though, if you're a perfectionist, is we'll go ahead and normalize that tracking generator output, and what that means is that any irregularities in the output of that TG output is going to be compensated for when we go ahead and input that signal to the filter, so that it is in fact going to be exactly 0 dBm. So anywhere that the level was a little bit high, it'll remember that and actually subtract off a little bit, and anywhere is a little bit low, it'll also remember where and the amount, and it'll add a little bit. So we go ahead and press normalize. We tell it yes. As it makes its sweep across, and by the way, it does that in 9 seconds, which to do a 1 gig sweep at 30 kilohertz is pretty impressive. So now it's normalized. It's all set to go. We go ahead and we'll unscrew that. We screw on the Microwave Associates low pass filter, and we'll go ahead and screw him on, and in just a few seconds there is a beautiful display, frequency response of this filter, and it's just awesome. Next thing we want to do is let's take a look at some of the markers. So right now it defaults to 1 marker right in the middle of the span, so right at 500 meg, and it gives you the relative value compared to the tracking generator level, which was 0 dBm. So right there at 500 meg it's down about minus 1.9 dB. Let me see if that's let's see if I can get you a little bit better. There we go. Okay, there we go. That's a little bit easier to see, and there we go. So what's neat is I can take the little cursor wheel and I can move it around to whatever frequency I want, or I can just enter in a frequency directly. So let's say I wanted to find out this low spot here. I wanted to find out in the passband what that level was. So I use the cursor wheel to come over here. At about 244 meg, I see the response is down 4.6 dB. Let's say I wanted to see set up another marker. I come over here, select marker number 2. It just enabled it right there, and let's bring it down. Let's see, right about there is minus 3 dB point. So you can see at 508 meg the response is down about 3 dB, or if you want you can come down to minus 6 dB point, and it's about 524 meg. That frequency display, by the way, is accurate down to 1 hertz. And this thing has inputs on the back for a 10 megahertz reference source. So if I wanted to, I could use my GPS based frequency standard, and so far I haven't compared the accuracy of the internal source with my GPS source, but maybe that'll be a cool thing to play with later on. Let's say you wanted to set up another marker, and we wanted to see what the ultimate stop band attenuation was. So we go ahead here, set up marker number 3, enable that, and well, rather than using the thumb wheel, we can see it's right around 900 meg. So this is what I was saying, you can just punch in the frequency directly. Just go 900 meg, and there it is. There's the level. But if you wanted to fine tweak it a little bit, move it over a little bit. Now here's a really cool feature. I love this part here. I've got 3 markers set up. I could set up a 4th one if I wanted to. Let's say I wanted to set up the 4th one, and let's say I wanted to see just how good it was way back here at some low frequency, let's say at 25 meg or so. So you can see at really low frequencies it's got extremely little insertion loss, like 0.05 dB. What's really cool is down here. It's got a function called a marker table. I go ahead and enable that, and how cool is that? It sets up a table showing you all the markers, gives you the frequency and the amplitude in a table format, and then compresses the plot so that both can be shown on the display here. So there you go. That's how easy it is to set this up and to measure the frequency response of some unknown filter. So I'm going to go ahead and pause this for just a second. I'm going to bring in another filter, and we'll do the same thing here. Alright, so this next filter is like a Frankenstein filter compared to this little Microwave Associates. This filter here I designed and built for a solid state 1 kW power amplifier for our 6 meter band, around 50 megahertz. And this is an interesting filter project for me because it had to have a very low insertion loss, and it had to have pretty steep skirts and have a lot of ultimate stop band attenuation, because the solid state power amplifier that I'm using, it's a Harris, it's a surplus Harris PA, was actually pretty dirty from a spectral content. The harmonics were not suppressed a whole bunch, and I wanted to make sure that I was compliant with FCC regs. So this is a great way to measure the filter response and make sure that we're compliant. So I went ahead and designed and built this. Let's go ahead and hook it up. Do the same thing here. Let's see here. We'll hook up tracking generator output here. There's the spec GAN input there. Now I want to look at up to about the 10th harmonic. I went ahead and looked at the power amplifier with the directional coupler, and I noticed that there were no real emissions above the 10th harmonic. So what I can do is go back to frequency here, and for the stop frequency, let's go ahead and pick 500 meg. So that'll take me up to the 10th harmonic, and there's the frequency response of that filter. Let me go ahead and zoom in a little bit. Alright, there we go. So you can see the filter response looks pretty good, actually. Looks like I've got a nice flat pass band, and if we take the cursor here, oh, that's the stop frequency. Let's put him back at 500 meg. And we'll go ahead and hit marker. And now I'm going to punch in a frequency, since I know I'm going to be transmitting at say 50.2 megahertz. I'll go ahead and oh, I got to enable that is what I got to do. Jeez, oh Pete. Okay, so there's marker 1. And let's punch in a frequency of 50.2 megahertz. There we go. So there's the insertion loss at 50.2 meg. It's about 0.31 dB. That's a little bit higher than what I really would like to see. It may not seem like a lot, but when you're passing a kilowatt through a filter like this, every 1/10 of a dB can actually be pretty significant. I'm actually going to be dissipating about 50 or 60 watts inside that filter. So when I built it up, I used number 10 solid silver coated wires for the inductors, and pretty beefy transmitting capacitors that were able to handle quite a bit of current and things like that for the C values. So between the L's and the C's that made up the filter, I know I'll be able to dissipate cumulatively a total of 50 or 60 watts. So, but that shows you right there what it is. Let's say we wanted to check out the what the insertion loss was at some of the harmonics. So I go over here to number 2. We turn on another marker, and let's say I wanted it. I know that on that amplifier the third harmonic was actually pretty nasty. So let's punch in 150.6 megahertz, and there we go. So the third harmonic shows that I'm down almost minus 54 dB, and that actually is really good for my needs, because given the output level of that harmonic from the amplifier itself going through this filter here, I'll more than safely meet the FCC requirement that all the spurs and emissions, harmonics, things like that are at least minus 60 dB down or minus 60 dBc. So this filter here will work out just perfectly. And you could do the same thing. You could set up another marker here and set it up for another harmonic. You know, I could go to some frequency. You know, let's say I wanted to see what it was at you know, 400 megahertz. You know, I could pick whatever I want. So there's 400 meg, and it's way down there. And again, I can turn on this table function, and I can see what the different values are. So it's really slick, just amazingly powerful. Let's say we wanted to take a closer look of the passband. We could go ahead and go back to the frequency. We could hit a stop frequency, and let's make it go up to say 100 megahertz. So there we go. There's frequency response now, and let's go ahead and turn off some of these markers since we don't need all of them. Let's turn off number 3, and let's turn off number 2. Okay, so now we're looking at just marker number 1. So you can see down at really low frequencies, I'm down at about 1 or 2 tenths of a dB. I'm really good, and it's not until, well, it's pretty flat really all the way. Well, there's some, luckily I don't have to transmit down at 40 meg, but right here at 50, yeah, there we go. And I can punch that in. I can make that 50.2 megahertz. Well, there we go. There's a more accurate look of what the insertion loss is. So I'm looking at now half a dB. And what I can do also is I can expand the y-axis here. Rather than 10 dB per, I can make it 2 dB per and get a very accurate look of what that is. So actually that 0.5 dB of insertion loss means that filter is going to be getting pretty warm, which is why I've got a lot of holes. I've got vent holes on both sides of it, and I'll be actually mounting a small quiet fan so that I move air through the components to keep everything nice and cool, because that'll actually be dissipating at least 60-70 watts of power. And I, you know, given this information, I may want to go back and tweak my design a little bit to see if I can't lower the insertion loss a little bit. So anyway, it's just that simple to use the tracking generator function on this. Incredibly easy, and something I hate to admit. I know this is bad, but I haven't read the manual. I just pulled this out of the box, and I'm starting to play with it, and it's so intuitive, it's so easy to use that within minutes, you're up and running and can be making some really useful measurements. So let me go ahead and cut this off, and let's see if I can do maybe one other thing. Alright, so I just set this instrument up right now to do a sweep from 9 kilohertz up to 2 gigahertz, and I just went ahead and did what I showed in the beginning. I just went ahead and normalized the tracking generator signal, just using a short piece of coax between the TG output and the spectrum analyzer input. So we're all set up here. Oh boy, let me get that phone here. Alright, so you'll have to excuse me, that was the telephone. So anyway, we're sweeping up to 2 gig. Tracking generator's been normalized, and what I'm going to be doing here is I've got a little El cheapo 10 dB attenuator. So every ham's got tons of these things, and let's say you just bought one off eBay, and this thing's rated DC to 3 gig, and let's say you just wanted to make sure that it is what it's supposed to be, and it's real easy to verify with this instrument and a tracking generator output. We probably want to change the y-axis scale here rather than 10 dB per. We don't need to, since we know that we're going to be measuring 10 dB of attenuation. We can go ahead and just change that. So we hit amplitude and the scale per division, and why don't we just make it heck, let's make it 2 dB. So we're looking at 2 dB per division now along the vertical axis there. So as simple as that, we unscrew the RF input, and we screw on the attenuator, and we watch it draw a picture. And there you have it. So you can see, make sure we're zoomed in all the way. We are. You can see the 10 dB line is right there. So this attenuator actually has just a little bit over 10 dB, and like every component, it's got a tolerance rating, and this attenuator could be plus or minus 1 dB, which isn't too far off from for what I paid for it. It probably is within spec, but you can see it for the most part. It's pretty flat, and it's just over 10 dB, and you can actually see the actual value. You can pick different frequencies, and you can see it's 10.6 dB right at 1 gig, and we can do the same thing. We can set up different markers, and we can pick whatever frequency we wanted to. And we do the same thing. We can turn the table on and see what the different values are. So that attenuator, is within 1 dB of being 10 dB, but this way you know exactly how much attenuation is at every frequency. So if you're doing something specific, say at 1296 or up at 432 or whatever, and you need to know exactly what the attenuation is, this is a lot easier and more accurate than setting up a a signal generator and putting in a signal manually and then recording the output, spot frequency. So in place of this attenuator, very easily could have been a length of coax. Let's say I've got, like I do, I've got a bunch of jumper cables, or I've got a length of coax, and you're not sure if it's good, or you're not sure if you put the connector on right, and you want to see what the insertion loss of the cable assembly with the connector is. You do exactly the same thing. You just put it in place of this jumper, and it'll show you what the attenuation is versus frequency. So that tracking generator is really unreal. It's just a super useful tool. And on this analyzer, believe it or not, the tracking generator you can get for like $160 or $170. So absolutely recommend the tracking generator output for that for this spec can. So anyway, that's my introduction to this Siglent SSA-3021X. I hope you found it useful, and we'll see if we can come up with some more videos on some neat things to measure with this fine instrument. So this is W8 BYA. We're off and clear. 73.